In this second video on the mechanical methods for nanomaterials elaboration, we are going to consider high pressure and high temperature methods that use very reduced volumes for the synthesis. Of course, we are speaking about the diamond anvil cell, and the volumes that we are speaking about is about 10 to the power minus 4 cubic millimeters. So these are volumes that we can use for research, but not for applications. So we already have seen what is a diamond anvil cell. We have two opposite diamonds, and the sample chamber is confined between the diamonds and a hole drilled in a gasket. We apply a force, and then we can reach such pressures as up to 1000 gigapascal at maximum, but usually very easily between 50 and 100 gigapascal. We can use laser heating to get also high temperature conditions, or resisting heating, that means with heating resistance around the chamber to combine pressure and temperature. A small ruby chip that is inserted between the diamonds allows, thanks to its fluorescence, this doublet that we observe here, we can then obtain a calibration of the pressure in situ, inside the cell. So it is even possible to reach, I say, pressure that more than 600 gigapascal, even some say up to 1000 gigapascal, using a double stage diamond anvil cell. You see here, these are the diamond anvils, and in between them we have here two secondary anvils that are nanospheres that can be done with synthetic nanodiamond, which is harder than diamond. And with this device, pressures as high as 6 megabars or even up to 10 megabars have been proposed. I'm going just to give you an example of the engineering that can be studied with the diamond anvil cell. We have seen that with high pressure, carbon nanotubes can collapse. That is a radial buckling, and the pressure depends on the radius, and can need the use of diamond anvil cell to study it. If we continue applying pressure or combining pressure and temperature, then these deformed tubes are going to be broken, and we get a graphitized sample, so which with further pressure and temperature application will transform to diamond. So this is something that we have done in the lab, and it's possible the way of producing the more expensive diamonds, probably. Okay. Diamond synthesis is boring. Anyone can do it. But with our knowledge that we have acquired on the buckling of carbon nanotubes, we can do something smarter, something new, really new. So if you take a bundle of carbon nanotubes, you know that we can reduce if we reduce the diameter of the tubes, we are going to increase very rapidly the collapse pressure, because it depends on the third power, inverse power of the diameter of the tubes. So taking small tubes, we can then reach the condition to start to create sp3 bonds between the tube before collapsing or graphitizing, and this allows to create a new material with a mixture of sp2 and sp3 bonds, which can be very hard, for instance. So this material has not been really well synthesized up to now. There have been some trials, but due to the fact that it is very recent that we start to have bundles of tubes having all the same chirality or diameter, this is a path that needs to be explored. The opportunity is to mix diameters in a bundle, and then we will have some tubes that will collapse, others not. Then those collapse will graphitize, and then at higher pressures and temperatures we can create some sp3 bonds. What we have created in that case is a carbon-carbon composite that can also have very interesting properties. So these are some examples of how research with the diamond anvil cell can help us to envisage new kind of nanomaterials that afterwards can be implemented using other types of synthesis methods to reach, let's say, industrial compatible quantities.